Okay, so here's the test review. So we started out with degrees and radians, basically. Just ways of measuring angle in degrees and radians. And then we applied them using the unit circle in the second section. So from this first section, basically I want you to be able to convert radians to degrees. And, if I do give you an angle in radians, like say 4 pi over 3, it's going to be this percentage of pi. Remember, to convert to degrees, you're going to multiply by 180 and divide by pi. And the whole idea is 360 degrees is 2 pi radians, so you can simplify it down to 180 degrees is pi radians. So you can cancel this out and then do the math. It should come out so that these are nice even integer numbers. They don't have to be, but so if we took 180 divided by 3, that would be 60. 60 times 4 is 240 degrees. And then to go the other way, degrees to radians, you just go do the same thing but the opposite. So let's say 210 degrees, you would multiply by pi and divide by 180. Now these could be, you could end up having decimal numbers. These, like I said, these formulas are not restricted to integer or certain angles. It's universally applied and it's good all the time. So usually when we have something like this, a multiple of 10, a lot of times we can end up with a fraction. So instead of putting 210 times pi, I don't want you to do this, 210 times pi, the actual number pi divided by 180, you could get 3.665, and all that tells me is you know how to use a calculator. What I want you to do is to have some fraction of pi, so you would have the numbers here, 210 divided by 180, and then you want to simplify it down to the simplest fraction. So you could divide each one by 10 if you wanted to, and you'd get 21 over 18, but these also still have a common factor, which is going to be 3, so you get 7 pi divided by 6. 21 divided by 3 is 7, 18 divided by 3 is 6, and so this is the answer I'm looking for here, some fraction of pi. And you might say, well, can I just use my calculator? 210 divided by 180, I'd get 1.1667, and you're like, can I use what is that thing? The fraction converted. I guess you could if you wanted to. If you do that, you get 7/6. But just remember, I want this as a fraction. Okay. The next, in terms of the unit circle, I just want to make sure that you know how to use the unit circle. So I could give you an angle. I could say, what is the cosine? Actually, I wouldn't write out cosine. We just put COS. So if I said, what's the cosine of 7 pi over 6? Previous one. So you would look at your unit circle and you'd say, okay, the x coordinate is the cosine and the y coordinate is the sine. So I'd look for this angle, 7 pi over 6. Hopefully you'd see it on there. It's going to be right down here. This is 6 pi over 6. Then you get another. So this is pi over 6 between here and here. Anyway, this is 7 pi over 6. So all you'd have to do is read off the coordinates. And if you looked at the coordinates on the unit circle, you would have x is negative the square root of 3 over 2, and y is negative 1/2. So you're going to, once you find the angle, you're going to say, okay, the cosine is the x-coordinate. So the final answer here, cosine of 7 pi over 6 is going to be equal to negative the square root of 3 over 2. And again, what I'm going to do, you could plug it in your calculator, and just if you did the cosine of 7 times pi divided by 6, what you would get is, if you plug that in your calculator, you get negative 0.866 something something. And if you give me that answer, it's wrong. Okay, I expect you to be able to read the numbers off of the unit circle and know which coordinates correspond to which functions. Okay, so don't try to get away with that, because I'm not going to give you any breaks on it. Again, that just shows me you can plug numbers into your calculator, which is not too great a skill. Okay. Now, later on, we can use the we can do the inverse cosine and inverse sine and inverse tangent functions. So if I said, what's the inverse sine of negative the square root of 3 over 2? So, this is one of those numbers that we see all the time: half, square root of 2 over 2, square root of 3 over 2. And you remember x equals the cosine of the angle, y equals the sine of the angle. So now when I say sine, inverse sine, that means I'm looking for somewhere in the unit circle where the sine is negative the square root of 3 over 2. It turns out there are going to be two solutions to that. And so if you looked for where the y coordinate is negative the square root of 3 over 2, what you'd find out is there'd be two places here. And again, you can use a unit circle, but there'd be this point, which would have an angle of 240 degrees, and then you'd have this angle here that goes all the way around. That would be 300 degrees. So those are the angles in degrees. But you have to remember that the inverse trig functions have certain quadrants that they are appropriate for. And we talked about that in the lecture. So in this case, it would be this fourth quadrant solution, because the inverse sine goes from negative pi over 2 to positive pi over 2, or negative 90 to positive 90. So so again, what I would expect you to do here is use the unit circle. It says don't use the calculator. Now, one thing additional thing you might want to put on your unit circle, right now, the fourth quadrant angles that you have, you've got 270, 300, 315, 330, and then you have 360. Okay, so, and then the corresponding radians: pi over 3, 3 pi over 2, 5 pi over 3. Here you'd have 7 pi over 4, and this would be 11 pi over 6. So those are the radians. So what I would suggest is you write in negative 90, negative 60, negative 45, negative 30 that go along with these positive angles, as well as negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, and those are the radians. Because when you do these inverse trig things, especially the sine, inverse sine, and the inverse tangent, you're going to be able to find these points on the unit circle, but you're going to not want to use these angles between 270 and 360. You're going to want to use the angles between negative 90 and 0, or negative pi over 2 and 90. So if you write those down, you'll be in good shape. Another thing you might want to go ahead and put in your unit circle are the tangent values, which are not, those are not the x or y coordinates, but just so you don't have to memorize them or you don't have to do any further calculations. So I'm just going to do these again, and you can put them on your unit circle. So you've got pi over 6, pi over 4, pi over 3, and you might like t for tangent. So the tangent of pi over 3 is the square root of 3. The tangent of pi over 4 is 1, and the tangent of pi over 6 is the square root of 3 divided by 3. So those are the values for the tangent. And if you go into the other quadrants, you can use that information. You can write it down if you want to, but you might start getting too much stuff. But notice all students take calculus. So the tangent is positive in the first and third quadrant. So here the tangent at this marking is going to be equal to negative the square root of 3. And here the tangent is going to be equal to negative the square root of 2 over 2. And here the tangent is going to be equal to negative the square root of 3 over 3. So they have the same values, the same heights. And likewise, you can go back, you're going to have these 3 similar angles down here, and you're going to have 3 similar angles down here. So the tangent is positive in the third quadrant. And so here you'll have the square root of 3 over 3, 1, square root of 3, and then we have negative the square root of 3, negative 1, and negative the square root of 3 over 3. So those are all the tangent values. In case I asked you something like, what's the inverse tangent of negative the square root of 3 over 3? So you go up here and you say, okay, I remembered to do this. He told me to do it and I remembered. Success. So, the inverse tangent is good between negative pi over 2 and positive pi over 2. And that's actually theta, the angle. So we're just going to look at these two, the first quadrant and the fourth quadrant. That's what this is saying. You can see here, there's the tangent. So the angle whose tangent is equal to negative the square root of 3 over 3. You look it off the unit circle and you say, oh yeah, I gotta make sure I use the negative numbers, not the. So the answer would be negative 30 degrees and negative pi over 6 radians. Okay, so that's how you can use the unit circle to find sine, cosine, tangent. You can basically find all of the 6 trig functions using the unit circle. Okay, so that's, I'm not going to ask you to memorize it. Okay, I will, another thing that I want you to be able to give an angle, find the coterminal angle between 0 and 2 pi radians, or between 0 and 360 degrees. So if I gave you an angle such as 724 degrees, and I say, what's the angle that's coterminal with this angle that's between 0 and 360? All you have to do when it's in degrees is just keep subtracting 360. So if I do that, I'll get 364 degrees. Again, you can use your calculator, and hopefully I did that right. I'll just double check here. 724 minus 360. So it's 364. Well, that's still greater, so you're going to do it again. 364 minus 360, and I get 4 degrees. Okay, so that's the answer. If I gave you an angle in radians, say it's 51 pi over 3, then how would I do that? Well, you're going to subtract 2 pi because that's just equivalent to 360 degrees, but depending upon what the denominator is, I could rewrite 2 pi in terms of thirds. It would be 6 pi over 3. Take 2 pi multiply by 3, divide by 3, I'll get 6 pi over 3. So you could keep subtracting that. Or you could, if you wanted to do it a little faster, instead of just doing it one at a time, you could think, okay, what number multiplied by 6 would give me a number that's less than 51, but close to 51? Well, in this case, I'd say, well, 7 is 42, 6 times 7 is 42, 6 times 8 is 48. 48 is not quite 51, so I could do that. I could take 48 pi divided by 3. So it's any multiple of 6 pi over 3. So I get 3 pi over 3, which actually is pi. So that would be a coterminal angle that's between 0 and 2 pi. Okay. Likewise, I might ask you which quadrant something's in. So if it's just an angle between these two, 0 and 2 pi or 0 and 360, then you could look on your unit circle and figure out where that angle is relative to the the quadrants. First quadrant goes from 0 to pi over 2, and the second quadrant goes from 0 to pi over 2 to pi, which you can read off unit circle. Third quadrant goes from pi to 3 pi over 2. I guess I shouldn't have these equal signs in here, because if they're on the axis, they're not actually in the quadrant. And the fourth quadrant would be 3 pi over 2 and 2 pi. So, and then of course you can do the degrees, but I'll let you figure that out. 90, 182, 73, 60. Now, if the angle isn't originally in one of these quadrants, or isn't between 0 and 2 pi or 0 and 360, then you'd find the coterminal angle that is, and then look for the quadrant. Remember the signs of each one of the 3 main trig functions in the different quadrants. So that's all students take calculus. So you can remember that. You can make up the table that we did in class, which would be sine, cosine, tangent, and the 3 quadrants, 4 quadrants. And then you could put whether they're positive or negative. So the way you work this out is you've got 12 different possibilities, 3 trig functions, 4 quadrants. All of them are positive in the first quadrant. Second quadrant, the sine's positive. Third quadrant, the tangent's positive. Fourth quadrant, the cosine's positive. They either have to be positive or negative. So if they're not positive, they're negative. Wasn't some old saying, I think it's in the Bible, but it was also used by George W. Bush. If you're not for us, then you're against us, right? It's a by. It's one or the other. So it's either positive or negative. So if I asked you what sine is the cosine in the fourth quadrant, I'd go over to this table and I'd say, okay, here's cosine, the answer is positive. So this is important to know. Okay, then we talked about reference angles. So reference angles are always values between, so we call that prime, theta prime, between 0 and 90, or between 0 and pi over 2. And as a consequence, the way we calculate them is if you have an angle where you have the initial side and the terminal side. This is the angle theta. The reference angle is the angle between that terminal side and the nearest x-axis. So this would be theta prime. And again, if you need something to remember in the first quadrant, the angle is the reference angle, because over here the nearest x-axis is the positive axis. So yeah, that's good. The reference angle is equal to the angle. In the second quadrant, the reference angle is equal to pi minus theta. That's in this case. So, if this was 120 degrees, then this would be, or instead of using pi for in degrees, it would be 180 minus theta. So in this case, theta prime would be 180 minus 120, which would be 60 degrees, which is between 0 and 90. In the third quadrant, the reference angle is equal to theta minus pi, or it's equal to theta minus 180. So in this quadrant, third quadrant, that's how you would get the reference angle. And in the fourth quadrant, the reference angle is equal to 2 pi minus theta, or in degrees, it's 360 degrees minus theta. Now these apply if theta is between 0 and 360, or if in radians theta is between 0 and 2 pi. So if I gave you, if I asked for the reference angle, let's say what is theta prime of theta equals 800 degrees. Well, this angle is not, well, for one thing, we don't know what quadrant it's in, and it's also not between 0 and 360. So again, what we do is we'd find a coterminal. I'll put CT. So you'd have 800 minus 360, which is still going to be greater than 360. Subtract it again. So that's 800 minus 720, which is 80 degrees. Okay, so that's a coterminal angle, which is now between 0 and 360. And so that's the coterminal. And then you'd say, well, that's in quadrant 1, Q1. So I go over here, theta prime is equal to 80 degrees. Use the appropriate formula depending upon. So the first step is to get it coterminal. Okay. The next stuff is we've got the right triangle trigonometry, which isn't really not that much different than right triangle geometry, except you've got six trig functions, which I guess you can't have in geometry, but in this case you've got the sine of theta is the length of the opposite over the hypotenuse. The cosine of theta is equal to the adjacent over the hypotenuse. The tangent of theta is the opposite over the adjacent. The cosecant of theta is hypotenuse over opposite. The secant of theta is hypotenuse over adjacent. And the cotangent of theta is the adjacent over the opposite. So those are all the six trig functions. So, really all you end up with, and these are right triangles, so you got to make sure your triangles are right, meaning one of the angles is 90 degrees. And typically you're given 2 out of the 3 sides, and you need all 3 sides lengths to be able to calculate the trig functions just by plugging in the corresponding lengths of the sides. A lot of times you're given you're given two lengths, and you have to calculate the third one. You know, this is the hypotenuse, this is the opposite, this is the adjacent. Here's your right angle. So let's call this x. This is the unknown. Well, the Pythagorean theorem says x squared plus 7 squared equals 10 squared. X squared plus 49 equals 100. X squared is equal to 51. X equals the square root of 51. So once you've used the Pythagorean theorem to get the third side, three sides of the right triangle, then you can then just plug into these equations. Now I am expecting you to, if any of these ratios have a square root in the denominator, then I'm expecting you to correct that. So in our case, the one that involves, in this particular case, it would be the where the adjacent is in the denominator. So it would be the secant and the tangent. So let's just do those two. So if I asked, you know, given that information, what's the tangent of theta, it would be equal to the opposite over the adjacent. So what I do is I multiply by the square root of 51 in both the numerator and the denominator. So that leaves 7 times the square root of 51 in the numerator, and the square root of 51 times the square root of 51 is 51. So that's the tangent, and the secant of theta is the hypotenuse over the adjacent. So again, I multiply and divide by that, so I get 10 times the square root of 51 over 51. All the other ones are going to involve the square root's already going to be in the numerator. So that would be where's the adjacent side is in the numerator. So here and here, those two are, they're going to involve square roots, but it's already going to have the square root in the numerator. And then the sine and the cosecant are going to be dealing with whole numbers. So that's pretty much it for right triangle geometry. I guess the other thing is, you know, we have those special triangles where we end up with the angles that are special when it comes to the unit circle. So we have the case of a triangle with equal length sides, and as a consequence the Pythagorean theorem says that this is equal to the square root of 2, and so, you know, the trig functions you get out of this are for 45 degrees, because if this is 90 and these two add up to be 90 and they're the same, the only solution is 45 degrees. So from this triangle we can, you know, we can see that the sine of 45 degrees is opposite over hypotenuse. But if you multiply and divide by the square root of 2, you'll get that, which is the number that we're used to seeing. And the other triangle that we have is the equilateral triangle, which then we break up into two equal parts. So the equilateral triangle is not a right triangle. So to be able to use it for right triangle geometry is to take it and split it in half here, and that makes two right triangles that are identical, and you've got this angle theta. Remember, this an equilateral triangle, all of the angles are 60. This is 60, that's 60, and that's 60. So as a consequence, this is 60, and this one is broken up into two parts, 30 and 30. So if we get rid of that now, we have a right triangle, and special because if this, each side of the equilateral triangle is 1, then half of the equilateral triangle is a half, and using the Pythagorean theorem, the third side here is the square root of 3 over 2. So those allow us to get the sine and cosine for 30 and 60 degrees. So even if you forgot the unit circle, you could use those triangles to come up with the values that we need. That's actually the way I remembered it, was through triangles, not through the unit circle or SOHCAHTOA. We also introduced these fundamental trigonometric identities in the trig section, because the right triangle section, because of the definition of the different trig functions, and because the sine was opposite over hypotenuse and the cosecant was hypotenuse over opposite, we have these reciprocal identities. And there are 6 reciprocal identities. So 3 of them are that. And then you have the corresponding ones where we just flip them around. So the cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. So those are all called reciprocal identities. Also, based on the definition of trig functions, in terms of their side lengths, we also have what are called quotient identities. And there you have the tangent of theta is equal to the sine of theta divided by the cosine of theta, and the cotangent of theta is equal to the cosine of theta divided by the sine of theta. And then finally, you can combine the Pythagorean theorem with these definitions, and you end up with these Pythagorean identities. Which turn out to be, all of these are very important. So you've got the sine squared of theta is equal to the cosine, plus the cosine squared of theta equals 1. If you divide this by sine squared, you get 1 plus cotangent squared of theta is equal to cosecant theta squared. And if you divide this by cosine squared, you'll get tangent squared theta plus 1 equals secant squared theta. So these are the 3 Pythagorean identities, which apply for right triangle trigonometry, but they also apply for any kind of trigonometry. The thing with right triangles is all the lengths are positive. Now, section 4 says trigonometric functions of any angle. And what they're talking about is they have some point in 3-dimensional space where you've got x and y. You know, this is positive, this is negative, this is positive, this is negative. And so if I define some point in space, you can draw an angle where the initial side of the angle is the positive x-axis, and the terminal side goes through that point, and this is your angle theta. Now, in terms of what this does is it generalizes the angles to something other than the ones on the unit circle. So this point has a y coordinate and an x coordinate, so we can show that it's y comma x. In this case, x is negative and y is positive. And from this, as well as the distance, so if you take the distance from the origin to that point, you call that r, the trig functions, instead of being defined in terms of lengths of a right triangle, can be defined in terms of the coordinates of that point and the distance from the origin to that point. So the first thing is r in terms of x and y is just, again, using the Pythagorean theorem. And r is always going to be greater than 0, because if you square something, it becomes positive, and then you take the square root of it so it stays positive. So this is r is always greater than 0, no matter which quadrant you're in. And then the definitions are that the sine of theta is y over r, the cosine of theta is x over r, the tangent of theta is y over x, where x cannot equal 0. Then we have the reciprocal of the sine, which is the cosecant. So it's r over y, where y does not equal 0. The reciprocal of the cosine is the secant, so that's r over x, where x does not equal 0. And the cotangent of theta, which is x over y, where y does not equal 0. So those are the angles associated with a point in space. So it's just a matter of, if you know the coordinates, you can figure out the radius. Once you have the coordinates and the radius, you can plug in and get the values. Now, because they're, if I said the sine of theta is equal to negative 5/9, and I said that we were in quadrant 3, I should be able to define all the other trig functions. So how do you do that? Well, the question is this negative 5 divided by 9, or is it 5 divided by negative 9? Well, obviously the denominator is r, so it definitely can't be that. So this says we have a negative x value, which means if we're looking in terms of the quadrants, the sign can be negative in the third and fourth quadrants. All students take calculus, so you can see the sign is positive in the first two quadrants, hence it must be negative. But it says it's in the third quadrant, so we can draw a line here down into the third quadrant, and we know r is positive because it's the distance, and you can draw a line here. This is going to be negative 5, and this distance is 9. So we can then take this triangle that we have like this in the third quadrant, but we're going to, and the angle is this angle. Okay, so that's the angle. But once we set up this triangle, we can kind of treat them as positive links to figure out what the other link is, so we don't get messed up. So the x coordinate, no, that's actually the y coordinate. So y is negative 5, because that's the now the angle is this, like I said, this angle, even though we think in this triangle that angle is a smaller angle. But as far as the dimensions are concerned, because the sine involves the y distance, we're going to put the 5 there. This is going to be 9. And instead of knowing x and y here and figuring out what r is, we know this, so we can find the x coordinate. We got the y coordinate from the sine, and we got the hypotenuse from the sine. So we'd say x squared plus 5 squared equals 9 squared. X squared plus 25 equals 81. Subtract 25 from 81, you'll get 46, I think. 81 minus 25 is 56. So x equals the square root of 56. So that's what this is. Now, once I've just used the Pythagorean theorem to get this length, what I'm going to do is I'm going to now specify these coordinates. So the coordinates would be negative the square root of 56. The y coordinate would be negative 5. So that's x comma y. R is 9. We were given that. So with these three things, you can go up and then just plug into this formula, as long as you have the signs correct, the signs of x and y, which I got because I was told that it was in the third quadrant. So they talk about reference angle in section 4, but we already talked about that. And the two kinds of problems that I'm going to ask you to do in this is I'm going to give you a coordinate somewhere here. I give you x and y. So let me just kind of write out what the kind of problems. So given x comma y, find all trig function values. And to do that, first find r, where r is equal to the square root of x squared plus y squared. And once you have r found, then use these definitions to find the trig functions. Okay, so that's the one. The second kind of problem is given the trig function, one trig function, given the trig function value, which, depending upon which trig function you're given, you'll be able to figure out what 2 out of the 3 sides are. So let's just kind of say if you're given the tangent is 12/5, what I can do from that is I can say, well, two things. I'd have to give you the trig function value, tangent of theta, not tangent of 12/5, but the tangent of the angle. So the tangent of theta equals, say, 12/5. I have to give you two things, given the trig function value and quadrant. So if I give you the tangent and I say it's in quadrant 2, what does that tell me? Well, it tells me that the tangent is y over x, and the quadrant it's in is the second quadrant, so I'm putting it right here, which means x is negative and y is positive. And actually that would have to be negative 12/5 if that's true. So if I gave you negative 12/5, if I didn't specify the quadrant, it could be either in the second quadrant or the fourth quadrant. But I'm given the second quadrant. What that means is if it's in the second quadrant, then I know that x has to be negative. So x equals -5, and y has to be the other sign, because the tangent of theta is y over x. So the numerator is 12, which is the y coordinate, and 5 is the x coordinate. Because of the negative sign, I don't know which one of these this goes with, but now I do. So I do that, and then I can calculate r, which is going to be equal to the square root of 12 squared plus -5 squared, which is going to be the square root of 144 plus 25, which is the square root of 169, which is 13. So then I've got r, I've got x and y, and then I can plug them into there. Okay, so that's if I gave you the tangent. Let's say I said it with the sine of theta was equal to -2/11. And I said it's in the, well, the sign is negative in either the third or fourth quadrant. So I say it's the fourth quadrant. So I draw a little picture here. I also look at my definition for the sine. The sine is y over r. So I've got y is equal to either plus or minus 2 y over r. R is 11. Because it's negative, I know that y has to be negative there. Now there are two quadrants where y is negative, third and fourth quadrant, but because I said it's the fourth quadrant, then I know that I'm going to have a y, negative y from this sign, and I would know that that x has to be positive, so this would be negative 2. The unknown x dimension is out here, and the distance from there to there is 11. So I would use the Pythagorean theorem to find x. So what I'd have is x squared plus negative 2 squared equals 11 squared. So I have x squared plus 4 equals 121. X equals the square root of 119. So now I know x, and I know it's positive. So with y equal negative 2, r equal 11, and x equal the square root of 119, then I can use these definitions here. So the whole idea is that I give you the coordinates and you just plug into the equation. Or I give you one of the trig functions and a quadrant, and you, from that information, you figure out what x, y, and r are, and then you plug into the equation. So that's the kind of thing that I'm looking for you to be able to do from that section. Okay, the next section is plotting sine and cosine functions. Went through a lot of those in class. I'll probably, not do more than 3 things at a time. Okay, because there's what things do we have? We have period, we have amplitude, we have x shift, we have y shift, we have x-axis reflection, and we have y-axis reflection. So those are the 6 possibilities. And I'm not going to do more than 3. But I think you should be prepared for any of them. So I'm just going to give you some examples here, what you might see. 2 sine of x over 2. So that has 2 things happening to it. The amplitude is 2. The period is 2 pi divided by this, which is a half. 2 pi divided by a half, which is 4 pi. So you would, I'll give you a piece of graph paper with this following, and we'll let you have it centered around the y-axis just to make it easier for you. So there'll be a graph that has 4 markings on either side. And then you'll have some kind of a scale up here, and you just have to figure out what that is. So to do the x scale, you just write the period in on the positive side. You write the period in the negative side. Then you take that period and break it into 2. Take the half period, break it into 2, and then count. 1 pi, 2 pi, 3 pi. Once you have this side, you just do the opposite on the other side. So you get that. So that's your scale. That's all based upon the period. Then your amplitude is going to determine your markings here. So because I have an amplitude of 2, I'm probably going to put 2 there and negative 2. There's no y shift, so everything's going to be symmetric around the x-axis. I would draw these dashed lines to help guide me drawing it. I'd have to know what the sine function looks like. So I probably have on my cheat sheet something like this to show the sine, how the sine looks for 2 periods. And I'd probably have one for the cosine, which is going to look like this. That one's always the harder one for me to draw. Okay, so that's the cosine. This is the sine. So it's a sine, which means I'm going to go through the origin. After a quarter period, I'm going to go up to the maximum amplitude. Half period, I'm going to go back to 0. 3/4 period, minimum, back to 0. And then I could sketch this thing in. So it looks kind of like a sine wave, and then I would just follow this and say, okay, well, I'm going down here, so I have to keep going down. And then, you know, the quarter period, I go to the minimum, back to 0, back up to the maximum. So then I can just draw this thing in and give it a good sketch. So that's that particular example. I'm not going to go through all possibilities because there's a huge number of possibilities. So you just have to kind of understand the procedure. Let's do one more here. Let's say it's 7/2 cosine of 2x minus pi over 2. So the key thing is anytime you have an x shift is you have to factor out the coefficient in front of the x term. Now if you don't do this, you're going to get the x shift wrong. And if you get the plot right and you don't do this, then obviously you plotted it on your calculator and you didn't do what I told you to do. So if you factoring out the 2 means dividing by the 2. So you take pi over 2, divide by 2, which is the same as pi over 2 times the reciprocal of 2, which is 1/2. So I get pi over 4. So this is going to be minus pi over 4. Now in this form, you're going to have the right situation. You're going to have, so what is happening in this case? You've got an amplitude of 7/2. You've got a period equal to 2 pi divided by this constant. So you got a pi. And you've got an x shift equal to plus pi over 4. And that's because we have x minus the shift. So the shift is plus pi over 4. So again, I'm going to give you a graph. It'll be centered around the y-axis. If I was giving you this problem, I probably would give you 4 marks here. Upwards, 4 marks downwards. So that I'd go 1, 2, 3, 4, because 7/2 is 3.5. So you have -1, -2, -3, -4. Okay, next thing you do is the period. The period is pi, so I'd go plus pi minus pi. Then I'd break this up into 2, pi over 2, pi over 4. So half and half again. 1 pi over 4, 2 pi over 4, 3 pi over 4. Go ahead and break this up into 4 parts. Negative pi over 4, negative pi over 2, negative 3 pi over 4. Just those are the numbers over here. So that's the scale based on the period. Then you would draw a horizontal line that's at the amplitude. So that's 7/2, negative 7/2. Okay, so that's taking into account that. I've gotten the period in there. My x shift. So what I do is I'd think about the cosine function. The cosine function normally looks like this. Starts at 1, goes down. So normally I would start here and then we go down to here, to the negative, back to 0, back up here. So that would be my normal cosine function. But because I'm shifting this plus pi over 4, well, here's pi over 4, so this part's going to get shifted over to here. This point's going to get shifted over to there. This point will get shifted over to there. This point gets shifted to there. So this is what my curve is going to look like. I could plot half or plot one period to the right. You see I go through one full period, and this thing's going to be symmetric around the y-axis, so it's going to continue down to the minimum through 0, up to the maximum, back down, something like that. Okay. Okay, so that is basically it for 4 or 5. The only thing I guess else I have to say is that there might be a problem where I ask you just to verbalize, or not to verbalize, but to write down what the transformations are. You don't actually have to plot it, but I might ask you, what is the amplitude, the period, the x-y shift? Does it have x-axis or y-axis reflection? And then I might have some where you actually have to plot them. Like I said, I'll give you a blank plot with the appropriate tick marks on it. Okay, and then we skip 4-6 and we go to 4-7, and so these are the inverse trig functions. So it's pretty much, what you have to do, what you did for your homework. So the first one is using the unit circle. And the key thing about using the unit circle is to remember the x-coordinate is the sine of the angle, and the y-coordinate, I did it wrong again. The x-coordinate is the cosine, and the y-coordinate is sine. You'll notice I make that mistake a lot, and so it's something that, at least to me, I always think that why do I think that? The x-coordinate is the sine and the y-coordinate is cosine. Why do I get that wrong? I think it's because we think sine and then cosine, x and then y, but it's not that way. It's the opposite way, so that's why you have to think about it. The key thing about using the unit circle here is to make sure your unit circle has those negative angles shown on it. So, negative pi over 6, negative pi over 4, negative pi over 3. Because if I ask you to take the inverse tangent, the angle whose tangent is equal to -1, what I'm doing here is I'm looking on my unit circle, and I said, okay, I can write the tangent values in all through here, and what you'd find out is the tangent here would be -1, and over here the tangent would be equal to -1. So the question is, which is your solution? Well, because the inverse tangent, the range associated with the inverse tangent is from negative pi over 2 to positive pi over 2, I know it's this one. I know it's this quadrant. And I know also to use the negative angles. So it'd be negative pi over 4 or negative 45 degrees. Now with the cosine, if I say what's the inverse cosine of negative the square root of 3 over 2, question mark, remember the range of the inverse cosine function is from 0 to pi. So it's going to be in the second and third quadrants. Because if I look, if I look for a place where the x-coordinate is equal to negative the square root of 3 over 2, I'll get two solutions. I'll get one here, and I'll get one here. So in my coordinates, I'll have negative the square root of 3 over 2 a half here, and I'll get negative the square root of 3 over 2, negative 1/2 here. So both of these have an x-coordinate of negative the square root of 3 over 2, but the range says that it's going to be between 0 and pi. So in this case, I can just read it directly off the chart. This angle here is going to be it's going to be 5 pi over 6, I think. 5 pi over 6, or 150 degrees. Now, how did I do that without looking at the unit circle? Well, because this is pi. If I subtract pi over 6, because that's the closest mark to the negative x-axis, that's pi over 6. So if I take pi, which is 6 pi over 6, and I subtract 1, I get 5 pi over 6. If I have 180 degrees and I subtract 30, I get 150. But you can just read it off the chart. Okay, now if I give you, again, you can use arc. If I said, what's the arc cosine of negative 0.67? Well, let's not do that. Well, that's probably okay. You know, this is not one of those special numbers. So, and this is using a calculator. So these are all using the calculator. And what I'll expect is 3 results: degrees, radians, and multiple of pi radians. So degrees, mode equals degrees. You just got to get your... Now you don't have to worry about quadrants here because it's going to do it all for you. So if I put my mode to degrees and I do the inverse cosine of negative 0.67, I'll get theta equals 132 degrees, which is in the second quadrant. Okay. With the unit circle, I had to figure that out or remember that, but the calculator does it automatically. Here, you just have to make sure the mode equals radians. So all I do is my calculator, find radians, and then just use the inverse cosine of negative 0.67, which is 2.305 radians. The third number, I want you to take 2.305 divided by 3.14159 times pi. Now I wrote this out as a number to show you this is, I'm just doing a division. Everybody's calculator has pi in it, so just use pi. So if I take 2.305 divided by pi, that gives me 0.734 pi. That also shows it's in the second quadrant because, you know, the second quadrant goes from pi 0.5 pi to 1 pi, or pi over 2 to pi. 0.734 is between 0.5 and 1. So that's one nice way of this decimal thing helps you, is because it tells you, it confirms what quadrant you're in. Okay, and then the next thing is using kind of the combination of the trig functions and the inverse trig functions. So I'll probably give you an easy one like this just so you're paying attention. You know, if you take the sine of the inverse sine of 0.6, the answer is 0.6. Or if I take the inverse sine of the sine, so they're the same, except one's sine, one's inverse sine. If I said pi over 3, so the angle whose sine equals pi over 3, the angle whose sine is the inverse sine of the sine of pi over 3. So the sine of pi over 3 would be like the square root of 3 over 2. The angle whose sine has the square root of 3 over 2 within the limitations of the domain is going to be pi over 3. Now if I did something like this, if I did the inverse sine of the sine of let's say 2 pi over 3, the answer actually would be pi over 3, which is confusing because you think it should be 2 pi over 3, but remember, if I take the sine of 2 pi over 3, I'll get the square root of 3 over 2, but if I then take the inverse sine of the square root of 3 over 2, I'll get pi over 3, because the inverse sine is only good between, gives me an answer between negative pi over 2 and positive pi over 2. So I wouldn't give you that. I wouldn't try to be difficult about it. And then you've got these combination situations. So you'd say the sine of the arc tangent of negative 12/5. In these cases, you have the inverse trig inside the parentheses. So the way this works is you're going to, there's a number of different ways to do it, but the way I think you should do it is two things. One is take your inside function, so the arctangent of, and say that's some angle. Theta equals the arctangent. Then you would say, okay, use all students take calculus. Now, remember that the arctangent has a range between negative pi over 2 and positive pi over 2. So that means it's going to be in the first quadrant or the fourth quadrant, third quadrant or the fourth quadrant. No, that's, sorry. So the tangent is positive in the first and third, so it's going to be the second quadrant or the fourth quadrant. But that's from this negative. Okay, from the negative sign, it tells me that it has to be in the second or fourth quadrant. But the arctangent requires that it is in the fourth quadrant or the first quadrant. So this is saying Q1 or Q4. So it's in the fourth quadrant, because they're both here requirements. So what that means is that I'm going to have some situation like this, and so I can create the best thing to do is just to say it's a fourth quadrant. Okay, so use the sign here of this as well as the requirements for the range of the function to define which quadrant you're in. And then you can make up a right triangle with just positive lengths. So in this case, we're dealing with the tangent. Tangent of theta is opposite over adjacent. So we don't worry about the sign here. We got the sign taken care of in this quadrant information. So the opposite is 12, the adjacent is 5. The hypotenuse is going to be 12 squared plus 25 squared. So that's 169 squared 169, which is 13. So that gives you the hypotenuse. And so now when we finally take the sine of this angle, the sine of the angle. Now we're not figuring out the angle, but we can use this triangle here. The sine of theta is equal to the opposite over the hypotenuse. So from our triangle, the opposite is 12. Hypotenuse is the square root of 13. and we could multiply and divide by the square root of 13. So we get that. And really what we're doing is, with the triangle, we're getting the magnitude of the value. The actual sign of this angle theta it's in the fourth quadrant. So the sign is positive in the first and second quadrant. So the fourth quadrant is going to tell me that the actual sign is going to be negative the square root of 12. 12 times the square root of negative 12 square root of 13 over 13. And that's the answer. So let me kind of repeat that. Again, there's all kinds of different combinations, so you got to think about the procedure. First, use the inside of the argument of the inverse trig function to figure out which two quadrants that happens in. So the tangent is negative in the second and third quadrants. That's from this negative sign. Then you take the quadrants that the range of the inverse trig functions are valid in. So for sine, it's negative pi over 2 to positive pi over 2. Or negative 90 to positive 90. For the inverse cosine, it's from 0 to pi, or 0 to 180, which would be here, this pi over 2, negative pi over 2 to positive pi over 2 is first and fourth quadrant. If it goes from 0 to pi, then it's in the first and second quadrants, and the arctangent is good from negative pi over 2 to positive pi over 2, so it's quadrant 1 and quadrant 4. And then you find the common quadrant from those two, from this sign inside the argument and the inverse trig function. So then you have the quadrant, and you'll use that later to figure out what the sign of whatever these SIGN of this last question. You take the numerator and the denominator in this argument to make a right triangle. So this case was the tangent. The tangent is opposite over adjacent. So I get two sides. I can use the Pythagorean theorem to find the third side. Once you have all the sides, you can figure out what the magnitude of this final question is. What is the magnitude of the sine? Use the right triangle. So the sine is the opposite over the hypotenuse. 12 over square root of 13, or 12 times the square root of 13 over 13. Okay, so that gives you the magnitude. To find the sine, you go back to the quadrant. So we're in the fourth quadrant. The sine is negative in the fourth quadrant, so it's negative 12 times the square root of 13 over 13. Now let me just, how would you do this? How could you prove this on a calculator? Well, you could come up with your answer. So you've done it my way, shown all the steps in between. You have negative 12 times the square root of 13 divided by 13, and the decimal equivalent of this number, which is not what I want you, I want you to do it like this. But if you use your calculator, said I don't know how to, if this is the answer you give me, nothing else. I'm just saying, oh, he knows how to use his calculator. So to check that I did everything right, I go to my calculator and it goes sine, left parenthesis, the inverse tangent of negative 12 / 5, two right parentheses. So this is going to take the inverse tangent of negative 12 fifths, and it's going to take the sine of that, and if I get the same answer, then I know I did it right. So I have the sine of the inverse tangent of negative 12 divided by 5, and I get the wrong answer. Why is that? Oh, I must have done a mistake here, because that can't be the right answer. So let me see what I did. The reason I'm saying it can't be the right answer, because this has to be This has to be, oh, I figured out what it was. Sorry. You're like, oh, I did it again. This is not the square root of 13. This is actually 13. 12 over 13. I saw this 13. I automatically put square root. So the actual answer is 12/13. So if I do that, negative 12 divided by 13, I get negative 0.9231. And I got here, when I did it, just in one statement, I get negative 0.9231. So they are the same. But again, you can use this to check your answer in your calculator. But I want to see the work where you create a triangle. You write down what quadrants are associated with this sign inside the parentheses using All Students Take Calculus. Figuring out what quadrants the arctangent is valid in, finding the common quadrant, which you write down for future reference. Then use these values of the fraction to define two sides. Use the Pythagorean theorem to calculate third side. Figure out what the magnitude of the sine, or whatever this function is out here, by using the lengths of the triangle, and then using All Students Take Calculus to figure out, is the sign going to be positive or negative in the quadrant of interest. So I think that's it as far as the inverse trig function. So you got three things. You got to use the unit circle to do the inverse trig operation. One is to use your calculator to get three different types. Actually, the fourth one is to just do the simple acknowledgement that these are inverse functions. So that's a freebie. And then if they are different, where you've got an inverse trig function inside, which is different than the trig function outside, you got to go through this procedure.